This chapter is on solutions, which normally we think of solutions including something in a liquid, and so we will talk about that type of solution. And it is probably the most common that we'll see and deal with in chemistry, but there are other types of solutions. So we'll look at those. We'll spend a good bit of time in this lesson talking about how we express concentration mathematically and numerically. We'll look briefly at solubility and how it is impacted by the structure of the molecules, and then we'll also look at temperature at the end. So to get started, we'll just talk about the different types of solutions. One type of solution that kind of has its own category is a suspension, or what may be known as a mechanical mixture. A suspension is heterogeneous. So think of the term hetero meaning different. So in a suspension, you have two different parts of the mixture that do not combine well. For example, sand and water. So when you mix sand and water, you know that the sand is going to keep falling to the bottom, giving you two distinct parts of the mixture. The reason that this is known as heterogeneous is because at different parts or locations in the sample, you're going to have different properties. Okay, so hetero meaning different. So the size, the shape, the concentration of the particles can all vary depending on where you are in the solution. If you think about a sand and water mixture, at the top of the solution, you're going to have much fewer sand particles than at the bottom. So the concentration is going to differ from top to bottom, for example. In many cases, if you have a suspension, you can separate it through filtration. The reason that suspensions are called mechanical mixtures is because you have to use some mechanical force, like mixing, to keep the mixture together. A good example of this is orange juice with pulp. You know if it sits in the fridge that most of the pulp is going to fall to the bottom. So what do you do before you drink it? You shake it. You use a mechanical action. But it's going to fall right back out, right? As soon as you set it back down, gravity is going to start to do its work. So suspensions don't stay suspended. The particles fall out slowly, which is why it's a heterogeneous mixture. There's going to be distinct parts of that solution. Right. However, a solution, okay, and I may have just used that word incorrectly before, because a solution cannot be heterogeneous. So orange juice with pulp is not a solution, although we may use it in that way. A solution is a homogeneous mixture. Now, homo means the same, but I don't want you to think that that means that there's only one thing in there, okay? It's still a mixture. So you still have two or more substances that are mixed together, but the way they combine makes a smooth, homogeneous, the same throughout mixture. So from top to bottom, the concentration is the same. From top to bottom, the particle size is the same. From top to bottom, everything about that solution is the same. If you make some Kool-Aid, the first glass should be the same as the last glass, if it is a true solution. Okay, so these things are the same top to bottom. That doesn't mean that there's not two things in there. Okay, so don't get that terminology confused. But it means those two things combine in such a way where you really now have one distinct substance, the same throughout. The components, therefore, cannot be separated through a filter. Cannot be separated through a filter if you have a true solution, because they have these intermolecular forces that are holding them together. So if you want to separate a solution, you've got to do it using something that will break intermolecular forces. Now, not bonds, okay, but you need to break intermolecular forces. So let's kind of highlight that. So to separate mixtures, this is what we got to do. We've got to alter those intermolecular forces. So some ways we can do that, and we'll look at these later. So make sure you note what they are as we go through the lesson. Distillation and chromatography, and we'll talk about those at the end of the lesson. Another distinct component or property of a solution is that none of the pieces in there are large enough to scatter light. So if you shine light through a solution, the light should not be scattered. And we can look at some images of what that means. But in a suspension, the light will be scattered. A good example of a suspension is fog. So if you're driving in fog, you've seen your headlights, they're being scattered. And so you can actually see your headlights in the fog as the fog scatters the light. If you're driving in the middle of the day, there's still air in front of your headlights, right? But it is a solution of air, a homogeneous mixture, so it doesn't scatter the light. But fog does because it's a suspension. All right, in a solution, you have both a solvent and a solute. So these are important vocabulary terms. The solvent is the one that is more plentiful. The solute is the one that is less plentiful. Now, most of the time, our solvent, if we're dealing with liquid solutions, is going to be water. But that's the case, but it is a very common solvent. And then your solute is just whatever you have less of. So you can have a mixture of iron and carbon to make steel. In steel, you have more iron than carbon. So iron is your solvent and carbon is your solute. So you can see it doesn't have to be a liquid. It doesn't have to be water. In air, the air that we're breathing is made mostly of nitrogen. So nitrogen is our solvent, and then the oxygen and the hydrogen and the, what else is in the air? Probably some water vapor, etc. Those are going to be our solutes. Most solutions will only hold a certain amount of solute. So when the solvent, that's the one you have more of, has dissolved the maximum amount of solute possible, then we call that solution saturated. That's as much as it'll hold. Now this is dependent on temperature. So if the temperature changes, it may be able to hold more or less solid particles. So if you think about when you're making sweet tea, you usually try to add the sugar when the tea is warm. If you go to a restaurant and get unsweet tea and then try to add the sugar when they've already got the ice in the glass, you're not going to be able to get that sugar to dissolve as well. So temperature plays a role here. But when the solution has the maximum amount that it can hold of the solute, then we call it saturated. And you'll know that something's saturated because there'll be some solid particles that are undissolved because the solution can't hold them. So if you see solid particles at the bottom, then you'll know that something is saturated. Once a solution becomes saturated, it is an equilibrium system. And remember, in equilibrium, the process is moving in forward and reverse. So some of this solid is dissolving, and then some of the dissolved solute is forming solid. The amount right here stays the same, right? In equilibrium, your concentrations don't change, but the rate is equal going in and out of solution. All right, let's kind of breeze through the types of solutions. So just think about how we have different phases of matter, solid, liquid, and gas. So we can combine those to make solutions. So we can have two liquids that are mixed together to make a solution, such as methanol and water. Methanol and water both have hydrogen bonding. So they can just hydrogen bond with each other. So water can hydrogen bond with another water, or it can hydrogen bond with a methanol. It really doesn't have a preference. Because of that, we say that these two are miscible. That means you can put as much methanol in water as you want, or as much water in methanol as you want, and they will never become saturated. There's no maximum amount. They will just keep mixing together. This is because of their intermolecular forces, their favorable intermolecular forces. Okay, you can read that note at the bottom. It is kind of interesting that if you put 2 milliliters plus 2 milliliters of methanol in water, you may not get 4 milliliters. So in chemistry, 2 plus 2 doesn't always equal 4. Those intermolecular forces may actually pull the molecules closer together. So 2 plus 2 may equal 3.75 in terms of milliliters. Remember, we do have the conservation of mass law. So if you add 2 grams and 2 grams, you got to get 4 grams. But volume can actually change. So just an interesting note there. All right, still dealing with liquids and liquids, we have another example. This is a different alcohol. You can see this one has a longer carbon chain attached to it, and it's being mixed with water. This alcohol is called hexanol, and because it has hydrogen bonding, it will mix with water, but it will not mix indefinitely. So if you add so much hexanol, you're going to reach a point where no more hexanol can be added. So we say that they are not miscible. Okay, they can dissolve in one another, that's fine, but they're not miscible. And really, when you hear the word miscible, you want to think like infinite. So you can't add an infinite amount of hexanol and expect it to dissolve in water. The solubility is limited. So it is soluble in water, but the solubility is limited because of that non-polar chain. So hydrogen will, on the water, will hydrogen bond with the OH group on the hexanol, but then it has all this chain that it can't hydrogen bond with. So that non-polar chain limits the solubility. All right, still dealing with liquids and liquids, we now have hexanol and hexane. So you see that they both have a long carbon chain. Now hexanol has that OH group, so that has some hydrogen bonding, but because they both have that long carbon chain, they both can form strong dispersion forces. So those strong dispersion forces will interact with one another, and those two are miscible. Not only are they soluble, but they're miscible. You can add an infinite amount of one of those to the other because of favorable intermolecular attractions. So when we're talking about solutions, we're really thinking about the intermolecular forces still, just like we were in the last chapter. So how strong or how favorable are the intermolecular forces between these two things? Well, in these two substances, hexane and hexanol, they both have those London dispersion forces. So that's going to be a favorable combination. In water and hexanol, they have some favorable interactions, but it's not completely favorable because of that nonpolar chain. So they're soluble, but not infinitely so. And then going back one more, methanol and water, they both have that hydrogen bonding, and methanol just has that tiny nonpolar region, so it doesn't affect the intermolecular forces as much, and so those are infinitely soluble in each other. All right, moving on to another type, we can dissolve a solid in a liquid. For example, salt will dissolve in water. So there are 3 types here of solid liquid solutions. We have an ionic compound that can dissolve in a polar solvent like water. So that is going to create your ion dipole attractions, and those are favorable, so we can create those types of solutions. If you have a polar solid like glucose, it will dissolve in a polar solvent like water. So there we'll have dipole-dipole attraction, or if the solid has hydrogen bonding, we may have hydrogen bonding with the water. That is a favorable interaction, so a lot of polar solids will dissolve in water. But non-polar solids are not likely to dissolve in water because that would not be favorable. So if you have a non-polar solid like a mothball, you're going to need a non-polar solvent so that they would interact favorably. And what intermolecular force do non-polar things have? They have that London dispersion force. So that would be the interaction between the two. We can also form solutions between gases and liquids. For example, in a carbonated beverage. You have your carbonated beverage, which is made mostly of water, and then you have your syrup in there. And so that's an example of a liquid-liquid solution. And then you have your carbon dioxide, which is a gas, added to that solution. Now, the reason that carbon dioxide will dissolve in water, even though carbon dioxide is nonpolar and water is polar, is because they actually form a new compound. They'll form this carbonic acid. So this is polar, and this is nonpolar, but they'll dissolve and make this compound. Oxygen can also dissolve in water, even though it's nonpolar, but its solubility is greatly dependent on the temperature. And so we'll talk about the role that temperature plays later on, but the temperature is important in oxygen dissolving because of the fish in the water. So with global warming, it's a concern that as the temperature of our waterways rise, there'll be less oxygen dissolved in the water for the fish because they breathe the oxygen that is dissolved in the water. Obviously, they don't come up to the top to get the oxygen. Okay. Another type of solution is a gas-gas solution. And gases, because of their motion, they are infinitely soluble in one another. So you can mix as much gas as you want to with whatever other gas. So we talked about the air that we breathe. We've got nitrogen, oxygen, carbon dioxide, water, hydrogen, etc. In the air that we breathe, it's mostly nitrogen, so that'd be the solvent, and then you have your other solutes. But that's an example of a gas-gas solution. All right, some other types of solutions are gas in a solid. Small gases like hydrogen can actually occupy the space between metal atoms. So for example, hydrogen can get into the spaces between iron atoms or palladium atoms. And you see that in the image there. And notice the distinct difference in the size of your metal atoms versus your hydrogen atom. So hydrogen can actually occupy the spaces between. So that's a gas-solid solution. Another type of solution is a solid-solid solution. And this happens mainly with metals. And so I want to point out a few key terms here. The first is alloy. An alloy is a mixture of two metals. A mixture of two metals. And there's two types of alloys that we need to be familiar with. The first type of alloy is an interstitial alloy. And the key word here is inter. What happens in this type of alloy is that some element fills the space between metal atoms. So this could be any metal here. And then some element, it could be a metal or a non-metal, fills the spaces between them. So here we have carbon occupying the spaces between these iron atoms. Now what that makes is steel. Okay, so this is how steel is produced. We have iron atoms, which are a very large atom, and then carbon comes and occupies the spaces in between some of these iron atoms. So what difference does that make? Why would we want to use steel instead of just using iron? Why is this interstitial alloy better? And here are some key properties of interstitial alloys. If you have a pure metal, remember they lack directional bonds from the last chapter. So the bonding is not between the atoms. Okay, let's go back to that picture. Remember, in a metal, you don't have directional bonding like this or like this. There's no bonding directionally. Remember that you just have the sea of electrons, and all these nuclei are kind of floating in that sea of electrons. So there's no directional bonds. So therefore, iron is not very rigid. No metal on its own is very rigid. But when we make this alloy, when we create steel, steel is more rigid, it is less malleable, so less flexible, less ductile. And why is that? Because when the carbon atoms get in there, you now have some directional bonding. So carbon is bonding with these iron atoms. And this directional bonding creates more rigidity. So we would much rather have a steel beam in our house than an iron beam. because of this rigidity that's created by these carbon atoms interstitially dispersed. The density is also greater because we have those carbon atoms packed in there. And the carbon atoms don't make the iron move out, so our volume stays about the same, but we have more atoms packed into a space. So when you think about density, you want to think how many atoms are in a space. So when carbon atoms move in, we've got more atoms per space. So steel is more dense, more rigid, less malleable, less ductile. So steel is going to be better suited for building, etc., than iron. All right, let's look at another type of alloy. We're still talking solids. These are formed, how do you get two solids to come together, right? You've got to melt them and mix them and then let them re-solidify. But this type of alloy is called substitutional. And it's just like it sounds. You have one type of atom that's substituted for another type. So in brass, you have zinc atoms that are substituted for copper atoms. You still have your terminology of solute and solvent. So if you look at this picture, you can see there's a lot more copper. So that would be your solvent. But then some zinc was substituted as your solute. Because you still don't have directional bonding, because zinc is just another metal, right? And it's not like stuck in these spaces. So you still got the malleable and the ductile properties. So interstitial alloys are going to be stronger than substitutional alloys. Your density is going to be somewhere in between your two components. So again, it's not going to change the density except to kind of average the two. Whereas interstitial alloys, your metal, it has these atoms in between it now. It's going to be more dense. Excuse me. All right, we'll stop there. Review the types of solutions and be sure that you're very familiar with the types of alloys and that you can recognize them in a picture.